So far, we've talked about exponential relationships, which are quite common, things like population growth or bacterial culture. When the function is like this, it's very easy to solve for y. Today, we're going to look at logarithms, which are the inverse of exponential functions, and they're useful for situations where x is the unknown in the equation. And so what we say is that we can use the logarithmic function to represent it like this so that it looks like a line. And that is really what we're trying to do. We're trying to make it easier to solve, make it look like a linear function. So we can rewrite any exponential relationship using logarithmic notation. So 2 cubed equals 8. That is a true statement. We can also write it as log base 2 of 8 is equal to 3. Here we would say log base 5 of 25 is equal to 2. And this last one with just variables, we would say log base r of t is equal to s. So the base of the exponent and the base of the logarithm are the same. And we're just rewriting it so that the variable comes down out of the exponent. So this is our definition of the logarithmic function, y equals log base b of x. B has to be greater than 0, and it can't be equal to 1. And we say that y is the exponent to which the base must be raised to give the value of x. So the first thing that we're going to do is rewrite these in logarithmic form. So I'm going to change my base of the exponent to be the base of the logarithm. My argument of the log is the answer to my question, and that's equal to the exponent that the base has to be raised to give 16. So same thing here. I'm going to make the base of my exponent the base of my logarithm. My answer is the argument, and then my exponent is the right-hand side. Here, my base is 3. My original answer is 1/9, and my right-hand side of the logarithmic expression is minus 2. Here, I'm going to go back. So here I'm going from logarithmic form back to exponential form. So I'm going to say 2, the base of my logarithm, is now the base of my exponent, to the exponent 5 is equal to 32. The next one, I would say 8, the base of my logarithm, raised to the exponent of 2/3 is equal to 4. And the last one, 7 to the 0 is equal to 1, which is actually our first log property here. Log with any base of 1 is always equal to 0, and that'll come up a little bit more as we do some more practice problems. The next thing that we want to be able to do is to evaluate the following logs. So the first thing that I'm going to do is I'm going to set it equal to y. Once I've set it equal to y, I'm going to change it into exponential form. And then I can use any equation solving. Really, I'm using guess and check. What exponent do I need to raise 3 to get to 81? In this case, it's 4. So I would say log base 3 of 81 is equal to 4. The next one here, I'm going to set it equal to y. And I would say 2 to the exponent y is equal to 1/8. The answer to this question would be minus 3. And so then my final statement would be log base 2 of 1/8 is equal to minus 3. I'm going to keep going for a couple more examples. So this is equal to y. I'm then going to change it into exponential form. And then I can use guess and check to find the value for y. And then I know what my log expression is equal to. Here I've got fractional exponents and a fractional base. I'm going to set it equal to y, change it into exponential form, and then solve for my exponent, which gives me the value of the log. Here I've got 2 logs in my expression, so I can actually separate these and evaluate them individually. So I know that here I have log 6 of root 36. I'm going to set that equal to y. Then I'm going to change it into exponential form. And then I know that y equals 1 on this side. On the sort of right-hand side of my expression, I've got log 25 of 5 is equal to y. So here I'm going to change it into exponential form. 25 to the y is equal to 5. And here y would be equal to 1/2, which means my overall expression would be 1 take away 1/2. And so my log 6 root 36 minus log 25 of 5 would be equal to 1/2. So if we keep going, there's a couple more examples here. I'm going to set this equal to y, and then I'm going to change it into exponential form, and then I'm going to solve for y. The next type of question that you can see is solving for x. And so here we already have the right-hand side, and we're looking for the argument of the log. So I'm going to follow the same approach that I did before, and I'm going to change it into exponential form, and then I'm going to evaluate my expression. Here I'm going to repeat. I'm going to change it into exponential form. Here I'm looking for the base of the logarithm. So I need to raise both sides to the 1/3, or take the cube root of both sides to get my answer for x. And finally, this is the property that we saw before in the earlier example. I'm going to change it into exponential form, but I know already that x has to equal 1. You should be able to use your calculator to use logarithms here. Log base 10 is called the common log or common base. So if there is nothing written here, it means that it's base 10. So I can change this into exponential form by using 10 as the base. So here I would say 10 cubed is equal to 1,000. In the next one, I would say 10 to the exponent minus 1 is equal to 1/10. And the last one here, 10 to the exponent 1/2 is equal to root 10. Using your calculator, using the log button, you should be able to evaluate these to 4 decimal places. This first one should be 16532, and the second one should be negative 0.4559. The last thing that we're going to take a look at is a graph. And we are going to graph the exponential function first, and then the logarithmic function. So I'm just going to change these. We're going to use 2 to the x and log base 2 to the x, because that matches our exponential ones from before. In order to graph our exponential one, we're going to use our 3 key points: minus 1 and 1/2, 0, 1, and 1, 2. And I'm going to put those on here. So I've got 0, 1, 1, 2, minus 1 and 1/2. I also have my asymptote at y equals 0. And then I'm going to connect those dots here. My logarithmic graph is the inverse, and so all I need to do to graph those is to switch the order of my 3 key points and then plot those on my grid. So I've got 1, 0, 1/2 minus 1, 2, 1, and my asymptote also switches. Now it is a vertical asymptote at x equals 0. and then I'm going to connect these points here. And this is really the reflection about the line y equals x. The red line is my logarithmic graph, and the blue line is my exponential graph.